Okay, so let's look at the following example here. Let's look at, I want one period of the function to be f of x equals x plus 1, and the period goes from -1 to 1. All right, so this represents just one period of the function. So we're going to model this. Actually, we're going to find the Fourier series for this function. So if we're thinking about what this function looks like to start with, x plus 1 from -1 to 1 just looks like that, right? And when we're saying that that's one period of the function, we're getting this kind of a pattern. Just the same thing repeated over and over again. So that's what I mean by the major assignment. You're going to find the Fourier series. That's one period of your function. One heartbeat. That's one period of your function. You're going to find the Fourier series and it'll repeat it for you. Okay? That's the idea. All right. So remember your Fourier coefficients. Well, your first one, you have to find that constant term. So remember, your constant term is your integral. Well, it's in general that we have. Let me write it this way first. In general, you have your f of x is 1/2 of a naught, and then plus a1 cosine x plus a2 sine x. And then, likewise, you've got the A3. Oops, I got those backwards. Sorry. These are B's. Come on, erase. Come on. There we go. B1. Sorry about that. A2. B2. And so on down the line. Well, your A's... Well, your A naught is just your integral of your function. So remember last time we did integral from 0 to 2 pi of f of x dx. And there's a 1 over pi out in front of it. And that's because it matches the other. That's why we've got the 1/2 out in front. Then your an is 1 over pi, integral from 0 to 2 pi. Of f of x cosine of nx dx. And your b's are your 1 over pi, integral from 0 to 2 pi of f of x sine x dx. Now, again, the reason why we did this when we set this up was we used 0 to 2 pi because that was the period we started with, right? We divide by the 1 over pi out in front because that's we divide by half the period. Those are those coefficients we came up with doing the projection of the function into that subspace. That was when we did the dot. We defined that dot product, and then we found out that the magnitude of each of those vectors was square root of pi. So we had to divide by square root of pi, and then another square root of pi came out when we did the dot product, and that's why we got the 1 over pi out in front. Okay. In general, though, we don't always have to have a period of 2 pi. We can use whatever period we want. We can have whatever starting point we want. The things that will change, of course, is this integral will be over one period. Okay? So in the example that we're going to do, we'll go integrate from -1 to 1 because that's one period. And the numbers that are out in front here will be 1 over half the period. Notice that pi is half of the period, right? And then the last thing we have to do is make sure we change the period. Oops, I forgot my n on that sine x over there. We need to change the period of our sine and our cosine function. So going back to the example, I'm going to rewrite it down here so I don't have to scroll back up. We had x plus 1. The period here is 2. So what will all of our coefficients be out in front of those integrals? It'll be 1, right? Because it's half the period of the coefficients that are out in front. Okay? So in this particular problem, we don't need to divide by anything out in front. Okay? We don't need to divide by anything out in front because half of the period is 1. Okay? So your A naught here will just be the integral from -1 to 1. Like I said, we can start at whatever point we want. They told us to start this period at -1 and go up to 1. So here's one period of the function. Okay? F of x is x plus 1 dx. And we can do this integral, but I'm just going to do it in GeoGebra in a minute anyway. Turns out to be 2. So I actually did this before I came to class. So if I don't get 2 when I type it in GeoGebra, I did it wrong. Okay? All right. So then your ANs will be integral from -1 to 1 of x plus 1 cosine of nx dx. And your BNs will be integral from -1 to 1 of x plus 1 sine of nx dx. Not nx, sorry. I got to change the period. Sorry about that. I do need to adjust the period on the inside of those things. These still have period 2 pi, but I want the period to be 2. How do I change the period from 2 pi to 2? What do I need to put on the inside of the cosine and the sine functions? I need to divide out by pi to make it a 2, but to divide out by the pi, I really need to multiply by pi on the inside, right? So we need nx times pi here in each of these. Because remember, the formula for period is 2 pi over the coefficient is the period, right? So to make the period 2, I would need to divide by a pi to cancel the pi's, which means I really need to multiply by a pi on the inside. Okay? All right, so we have our formulas now, so let's just go over to GeoGebra and do it. Assuming GeoGebra will work. It's a big assumption.
That's n times x times pi. Right?
N times x times pi, yes. Or whatever order you want to put it in. Yeah. All right, remember you want to do this. To find the formula, if we're actually going to find a formula and not just get the coefficients individually, to find the formulas here, we want to use the computer algebra system window, not the algebra window. So make sure you use the computer algebra system window. So again, the first thing we're going to compute is the integral of just the function, which was x plus 1, and we want to go from -1 to 1. Hey, look at that, I got 2. And then let's do the next one. This is going to be x plus 1 times cosine of n times x times pi. And again, the reason we have to put the pi in there is because that adjusts the period from 2 pi to 2. So your starting value then is -1, and your ending value is 1. All right. Now remember, we're using the computer algebra system, so it'll do this symbolically with respect to x, but we know what the values of n are. GeoGebra doesn't. It's just treating n like any old constant. It doesn't know what you mean by the n, but it does understand that you're treating it as a constant because you integrate it with respect to n. But we know what n is. Well, what type of an object n is. What kind of an object is n? It's an integer, right? So you're plugging an integer in for n, so you're taking the sine of multiples of pi. What's the sine of any multiple of pi going to be? 0, right? So there are no besides the constant term, there are no a coefficients to this series. Those are all 0, right? Because I got sine of n pi. Those are all 0, right? We agree? Okay, so let's do the next one. We have x plus 1 times sine of n times x times pi. And again, we want to go -1 to 1. There's what we get. Again, GeoGebra is treating n like a constant, but we know what that constant is, at least what kind of an object it is, again, it's an integer. So that second term in the sum in the numerator is going to be what? 0 again, right? The first term is going to do what? Is it always 1? Is that cosine of n pi always 1? No, it's going, what's it do? Alternates, right? It flips between -1 and 1, doesn't it? So for that first one, if I write it here on the board, maybe, and I'll write it on the screen too, I just didn't want to flip screens. While I was here. That first one, you're going to have -2. Notice this n will cancel with one of them on bottom after we get rid of this term on the sum, right? This is 0. The second term is 0, right? So this n will cancel, one of those pi's will cancel, so we get -2 times -1 to the n over n pi. Those are your bn's. And again, I'll write this on the screen here in a minute because I want to show you how we play with these to get those series expansions like you have to do on the homework. Okay? But does everybody see where that's coming from? Well, maybe lack of light keeps you from seeing what's going on. But does everybody see where that's coming from? The sine of pi n is 0, no matter what you plug in for n. Cosine of pi n is alternating between -1 and 1. It's -1 when n is 1, it's +1 when n is 2, and so on. Right? That okay? Okay. So now, if we want to get a plot of what this looks like, this is when we can use, we have to define it as a function. So if you're going to define a function in the computer algebra system mode, you can use function notation like you always do. F of x, g of x. As a matter of fact, you can use whatever, you can use more than one letter as a function name too if you really want to. Okay. But I'm just going to use f of x because that's what we're typically used to using. You have to use colon equals to say that you're actually defining a function here. All right, so remember, I've got the constant term, you actually have to divide by the whole period. Remember, there's that extra 1/2 that's out in front of your a sub 0. Okay. Probably just as easy to remember to divide the constant term by the whole period and your other terms by your other coefficients by half the period. That's why when those examples that I sent out to you by email, I just did the integrals first and then did the division, just adjusted by whatever the period was. Okay. Whatever you want to do is fine, but I'm just letting you know that that's what the constant gets divided by the whole period, every other coefficient is divided by half the period. So our constant term here should be 1, because our 2 was the interval we came up with, right? And then it'll be plus the sum of, let's just do n equals 1 to 10. I should have left it open, but that's okay.
Which sum did you choose?
I chose. Sound like my nieces. The second one here. I want to do the sum. I'll just write it this way now. The expression I want, well, typically we would do number 2 times cosine of n pi x, and then number 3 times sine of n pi x. I'm going to go ahead and do that. It's unnecessary in this one because that one's always 0, right? But just to show you in general what it typically looks like, I would do number 1 cosine of n times x times pi, and then plus, nope, not number 1, number 2, sorry. Those were our coefficients for the cosine, and then I would do number 3 times the sine of n times x times pi. Number 2 is the coefficients on the cosine because I integrated the cosine piece. Number 3 is the coefficients on the sine because I integrated the sine piece. Now again, I really don't have to put in number 2 here, right? I could leave that first part. I could just have this not even be here. It would be the same thing. All right, the variable we want to sum up is n. And we'll start at 1, and let's say we just do the first 15 terms. So I'll do n equals 1 to 15. Or it may not be necessarily exactly 15 terms, and some of them turn out to be 0. We'll see examples of that in a little bit, but there it is, and there's the graph.
Okay, so the 1 is because we're taking whatever we get from number 1 and dividing it by 2.
Correct. Yeah. Yep.
So that might not always be 1. It just happened that we.
It just happened to be
1/2.
1/2 times the 2 is 1. Yeah.
So it's always 1/2.
It's always 1/2 times whatever the integral. It's always 1 over the period times the integral you get for the first one. So the first one, this one is 1 over the period. This one is 1 over half the period. So I would put up, if you were going to do this one and had a different number here for the period, I would just put the 1 over half the period out in front. That or put it in front of your integrals to start with, one or the other.
When we were doing our original integral, why didn't we include this 1 over pi?
Well, in this case, it's not 1 over pi, because the period is not pi anymore. It's not 2 pi anymore. The period is 2. The pi represents half of the period.
Mm-hmm.
In this case, the period is 2, half the period is 1. So I didn't need to have the, I didn't need to have anything.
1 over pi is just
It is 1 over half the period. Yep. So here's a graph of the Fourier series. It should look repetitive. So if I zoom in maybe a little bit here, you actually do see repeating pieces there, even though it looked a little goofy at the beginning. So the cool thing about this is that as long as you have a periodic function that is bounded, meaning no infinite discontinuities, and only has a finite number of discontinuities, your Fourier series is guaranteed to converge everywhere except at the points where it's discontinuous. What's even better is, where it's discontinuous, your Fourier series will go through the average of the two endpoints. So each of those spots where it's trying to connect the top to the bottom, right there at that point of discontinuity, the value of the Fourier series is the average of the two. So it'll be a half in this case. No, I'm sorry. It'll be 1 in this case because it's the average of 0 and 2. So any any periodic function that's bounded, so no infinite discontinuities. So not tangent, right? Tangent would be a periodic function, but has infinite discontinuities. Okay, that wouldn't be allowed. But any periodic function that is bounded and has a finite number of discontinuities always has a Fourier series that converges to the function, except at the point where it's discontinuous. Because it's trying to connect the dots with continuous functions at this point. Kind of not unlike what your graphing calculator does, right? If your graphing calculator has an asymptote somewhere in the middle, it typically tries to take the top part and connect it to the bottom part. Right? That's what this is doing. I still think it's cool that you can do this with trig functions, by the way. This is pretty fun. But you can kind of see why I wanted you to do the major assignment that I want you to do with the EKG. Questions on this one? Before I do the whole going into the series thing. So this is what I would expect you to do for the major assignment. You do not need to try to write down the closed form, a nice formula for your Fourier series. Some of them just don't have nice forms, and your major assignment shouldn't have a nice form to it. Okay. However, the one we just came up with does have a nice form. We just said that our Fourier series for this one is our f of x is 1, that was the constant, right? Plus, only the b sub n survived. So this is going to be the sum from n equals 1 to infinity of negative 2 over pi, that constant, times, wait a minute, something's goofy. No, maybe not. Negative 1 over n, negative 1 to the n over n. Times your sine of n pi x. Because only the b's survived, right? So the b's times those increasing multiples of pi x for sine. So this particular series now, we can use this to prove some other values. So we want to notice that this is going to be true. I just told you that every Fourier series will converge to the function it's representing as long as you're not at an endpoint. Okay? So for example, I don't want to put in 1 or negative 1 here because those are endpoints, right? Those are points of discontinuity for our f, correct? But any other value that I plug in, I will get a true statement. So one value you might try to plug in is 0. Unfortunately, 0 is not going to be a very interesting example here because what's going to happen to this series if I put in 0 for x? I get 0, right? And the only equation I get would be f of 0 equals 1, which I already know, because f of x was x plus 1, right? However, let's try to put in a different number. Let's say I put in f of a half, or put in a half for x, I mean. F of 1/2 by the formula is equal to, by the function definition is 3/2, right? Right? If I plug that in the right-hand side, right? So I get sine of n pi over 2. Think about what sine of n pi over 2 does. When you put in 1 for n, you get 1. When you put in 2 for n, you get 0, don't I? When I put 3 in for n, we get negative 1. When we put 4 in, we get 0. We put 5, we get 1, 6, 0, 7, negative 1, 8, 0. Notice only the odd terms survive, right? Right? Also notice that when you put in 1 for n, you get a positive 1 here and a negative 1 here, right? When you put in 3 for n, you'll get a negative 1 here and a negative 1 here. Notice that when you put only the odds in, you're only going to get negatives here, right? If all I put in for n's here are odd, I'm always going to get negative, correct? So that negative will take care of that negative, and this will alternate. So we can rewrite this as 1 plus the sum from n equals 1 to infinity. I'm going to pull the 2 over pi out in front, and this will be negative 1 to the n plus 1 over 2n minus 1. Only the odd terms survive, which is where I get the 2n minus 1 in the denominator. Right? Yeah? Do you see where the 2n minus 1 I got, why I wrote it that way? Because anything I plug in for n is going to be odd now for the denominator. Right? This is the only denominator that's going to survive up here. So I just wrote it as a bunch of odd denominators. And then we said that this alternated and the first one was positive because these two canceled each other out. So this negative 1 to the n plus 1 is representing the alternating nature of this for when n is odd. So a question, Morgan? I saw your hand start to go.
Yeah. How do you know n is only on?
Well, because anytime I put an even in for n, it'll cancel the 2 with this one, and this is going to be 0. Because it will have integer multiples of pi in that case. That's why I know that the even terms all get killed off. So only the odd terms are left. So we now have the equation. Still have this 3/2 on the left-hand side. I can subtract the 1 over. And then multiply by pi over 2 and get a nice series expansion for pi over 4. Which is kind of cool. Now, if you remember your Maclaurin series for inverse tangent, you get the same value, you get the same answer out of this. So this is how you play with the series to get play with the Fourier series to get series expansions for different, well, irrational constants in this case. So notice that your series on the right-hand side is just, if you wrote it out, it would be 1 minus a third plus a fifth minus a seventh. That converges to pi over 4. It converges very slowly, but it does converge to pi over 4. Which is pretty good. Want to see another one like this? All right. So let's do the following. Let's say we have, make sure I grab the right one because I wanted to do what I wanted to do. We want to do the Fourier series for f of x equals 0 between negative pi and 0. And it'll be sine of x, oops, that should say 0, not pi. It should be sine of x for 0 less than or equal to x less than pi. Because I don't really care if I have the equal to sign on the other one or not. What's the period for this one? 2 pi, right? So now we will have something to divide out in front. Your constant will get divided by 2 pi, and your constant term will get divided by 2 pi. Your other coefficients will get divided by pi, half the period. Okay? All right, so bump back over to GeoGebra, maybe. Let me just open a new window. And open the CAS. All right. So we want to integrate the function. Now, half the time it's 0. Do I really need to integrate the 0 function? What's the integral of 0? 0, right? So really I only need to integrate sine of x on the interval from 0 to pi. I don't need to integrate the 0 part because that's just going to be 0, right? We agree? All right, so let's do the next one. I want to take sine of x, the function, times cosine of n times x. The period's 2 pi, so I do not need to adjust the period, right? The reason why we put the pi in the other one was because there was a pi, or the period was 2, so I had to change the period. Okay, here the period's 2 pi, I don't need to change anything. 0 to pi. Now this one we have to be a little bit careful. A couple of things are going on. But notice that we can't plug in 1. for n, right? We agree? We can't plug in 1 for n here. So we actually need to handle that case separately. So let's just integrate sine of x times cosine of x. That would be when n is 1, right? Right? And go from 0 to pi. And notice we got 0. The reason why I noticed I had to do, remember when we did the sum command? The first number I plugged in was 1. If I did that here, it would return an error. Right? And be trying to divide by 0. Okay. So that was why I knew as soon as I saw that formula, I need to make sure that I did a different computation for n equals 1. So that's why I did that separately. Do we see why?
So how did you do that?
How did I do that?
I see like our problem with the 0 in the bottom.
So this is supposed to work for any n greater than or equal to 1, except it doesn't work when n is 1. So I had to check to see what the coefficient, that A1 coefficient is. I don't have a nice formula for A1 because 1 doesn't work in that formula. So that's why I had to do a different computation. It's kind of like when you do power rule for integrals. I can't use the power rule for x to the negative 1. Because if I try to add 1 to the exponent and divide by it, I get 0 in the denominator. So I have a different rule. Same kind of idea here. This is trying to give me a rule for the integral no matter what the n is, but the rule doesn't work when n is 1. Yeah, Grace.
Since our period is 2 pi now, why don't we have to put the 1 over pi?
We are going to. I'm going to do it at the end. Yeah, I just like to do it at the end as opposed to in the middle. You can, if you prefer to do it now, put 1 over pi in front of it. It won't hurt anything. Yeah, Chelsea.
When is it coming out, right? Did it on the last problem too?
Are you in the computer algebra system window? The CAS window?
Well, this one.
The reason why is because you started with an algebra window, and it's trying to treat n now as a slider.
Yeah, so why did, I thought I had the right one up though.
Did you type it in this window first, in the very beginning?
Yeah.
Yeah, that's what it caused it.
So
I would just kill GeoGebra and go back into it again and don't get it. You just close the algebra window completely.
So how did I open the wrong window?
It defaults up to algebra when you open it up. Okay, so go to view and then click on the Yep. You're welcome. The reason why is when it was typed in the algebra window, it made n a slider, so it actually has values for n at that point. That's what was causing the issue. All right, so now we need to do the other one. So I need to do sine of x times sine of nx from 0 to pi. What's that going to be every time? It wants to be 0 every time, right? Agree? So in this case, only the cosines survive. Because only the cosines give us values that are non-zero. All right, so if we're going to do this particular one, let's define it as f of x again, or whatever your favorite function name is. I have to do the constant divided by 2 pi, right? I gotta do the constant divided by the period. Period here is 2 pi, so I need 1 over pi for my constant. I need 1 over pi times my entire sum. Did I type an I? Did not mean to type an I. 1. All right, I'm just going to put the 1 over pi out in front of the sum. Because it's going to get multiplied by each of your coefficients anyway. All right, so we don't need to worry about number 4 here, so I'm not going to bother putting it in this time. I do need to worry about number 2, but I don't want to plug in 2 for n. Or, excuse me, I don't want to plug in 1 for n. I want to start the sum at 2 this time. So we'll take number 2. I'll multiply it by cosine of nx. Variable is n. I want to start at 2. And again, let's just do 15. What did I do? I did this last time. Oh, wait. Same problem. Ha! I forgot something. Of course I did. When is this formula not valid? When 1. I have to do that one separately too. Sorry about that. So if I do integral, I did the exact same thing in my office when I did this before I came to class today. I need to do sine times sine, or sine of x squared, right? Because you'll have sine times sine when n is equal to 1. Start at 0, end at pi. We get pi over 2. Now that is our, it's not quite our B1. Not quite B1, right? I got to divide it by pi. So I need to go back up here to my sum formula here and add in a 1/2 of sine x. There we go. That fixed it. The B1 term is the only one that survived, right? Because we said that whenever n was 2 or bigger, all of these were 0, right? You agree? All of these are 0. So whenever n is 2 or bigger, these are 0. So only the n equals 1 term survived for the b's. And I used 1/2 because the answer was pi over 2, and we divide by the period, which is pi. And look how nice that function came out, by the way.
Why did you change the 1 back into 1?
I just added 1/2 sine x. I just stuck it in between the two. Why did I add that in? This formula here does not work when n is 1, right? So I had to go back here and do this integral for when n is 1, get pi over 2. I have to divide that by the period, or by half the period, sorry. So that becomes 1/2, and that's the coefficient on the sine x. Because that's the coefficient on sine nx when n is 1. So it's 1/2 sine x, that's why I was in there. All the rest of them were 0. Yeah, Marshall.
Could you repeat what you put inside your expression for that summation?
Yes. Inside here?
Yeah.
Okay, so I put in, I did sum of number 2 times cosine of nx, and then n and 2 and 15. You're welcome.
Does the 15 make a difference? Or?
No, that is just, the more terms you have, the closer it'll be to the actual function. Because if I change it to, say I change it to, instead of 15, say I put a 6 in there instead. So you can see it's a little bit wavier here. Yeah, it's still pretty good here, but it's definitely wavy here, where that one's definitely flatter. So, the more terms you have, the better the approximation is. That's the idea. Yeah, Morgan.
Could you show how you get your first, like the 1 over pi, like your first term? Like where that comes from?
Where the 1 over pi comes from?
Yeah, like in front of the 1/2 side of x, like your A naught.
This one?
Yeah.
So the integral we got was 2, and we divided it by 2 pi, because that was the period. Remember your A naught, the integral that you get for just the function, you divide by the whole period. I didn't put the 1 over pi in front of the integral to start with. If I would have put 1 over pi in front of the integral to start with, you would have had 2 over pi, and then you would have multiplied that by a half. So that's where the 1 over pi, or the 1, over pi comes from. When you have, oops, this one here, I didn't have this in front of my original integral. In my brain, it makes more sense to just do the integrals and then divide out by what I need to at the end.
So instead of dividing one time by 1 over pi and another time by 1 over 2, you're just dividing by your
The whole period, yeah.
Okay. Is that only when it's from 0 to 2 pi? Or do you
No, that's every time you divide by the whole period. Yeah, it's every single time. Yep. Okay, so let's see if we can go through this again and come up with a series expansion. So we said, if I go back over to GeoGebra, we've got 1 over pi, 1/2 sine x, and then this piece here. Notice again, we've got this alternating between -1 and 1 here, right? And in particular, when it's -1, it makes this a positive one, and we get 0 again, don't we? So in this case, the only ones that survive are the even terms instead of the odd terms. Right? If you plug in 1 for n, or 3 for n, or 5 for n, you're going to get 0 in the numerator. So the only things that survive are the even terms in this case. So we get your f of x is 1 over pi plus a 1/2 sine x plus a 1 over pi series from n equals, I'll make it 1 to infinity. So I need, the top was a negative cosine nx minus 1. When I plug in 1, I'm going to get 0. When I plug in 2, let me start this at, no, I don't want to start it, that's fine. Start it there. You get a -2 and then a positive, or sorry, when you put in 1, no, the only thing that's going to happen is you're going to get -2 when it actually works, right? Because it alternates between 0 and 2. So this will be 2 over, and it'll be 2n squared minus 1 times cosine of 2nx. Because only the even term survived in this case. And I lost a negative sign. So we had -2. Because again, the top was negative cosine of n pi minus 1. So when cosine is 1, we get -2 on top. When cosine is -1, we get 0 on top. So it's always 2 when it survives. So the top is just -2. It's not alternating. The bottom, what I'm doing here is just expressing it as even terms. So I replace the n with 2n. Like we did before with the odd terms, we replaced the n with 2n minus 1, or 2n plus 1, depending on which way you want to look at it. All right, so then again, if we want to try to get a series expansion for something, I can plug in a value for x, and it has to be true on both sides. In this case, 0 is going to work really nicely. When I put in 0, what do I get here? 0, right? When we put in 0 over here, we get 1 all the time, right? So if I put 0 on the left-hand side, I get 0. We'll get -1 over pi plus 1 over, or I'll write it as minus here. Really, minus? Something's not quite right there. Yeah. Leave it this way this time being. I'm missing something in here.
Why did you put -1 over pi?
That was our constant term. Oh, it should be +1 over pi. Thank you. That made a difference. Somewhere along the line I've missed a term. Because things aren't canceling like they should. Somewhere there's a pi missing. I don't know where it is. I did this before I came to class too. If I move the series to the other side, something is off. What is missing? Now we write it as 2 over pi here. This should be a half on this side, so I'm not sure where I'm missing what I'm missing. Because there should be a 1/2 over here. It should be 1 over 1/2 of it, right? We got 2 over pi for our a sub 0. So something, there should be a 1/2 and not a 1 over pi over there, because the idea behind this is that we get another expansion for pi over 4. I'm missing something is goofy here. I have to go find it. Yeah, Kelly.
I mean, you put a sub 0, you put a sub 1. I mean, you did.
The a sub 1 was 0. Yeah. Yeah, a sub 1 was 0.
Why do you have a 1 over 2 sine x and then you're at 1 on your sum?
Say it again. Say it again. Sorry.
So we did the 1 over 2 sine x is f1, right? Because we couldn't take the.
That is b1.
So why is the summation starting at equal 1?
Because I changed it to be evens. I just rewrote it so it would be, I replaced n with 2n so I could start it at 1. That was why I did it that way. Here I just factored the denominator and made it 2n plus 1 times 2n minus 1, because I have 2n squared minus 1 is the difference of squares. So you can notice that this pi over 4 will be, there's a term missing. I know I would go back to my office and I'll find it. There's a term missing in here somewhere. Yeah, there's a 1/2 missing somewhere, period. I'm missing something. I don't know where it is. But anyway, you end up with an expansion that looks like the following. Plus a 1 over 1 times 3, a 1 over 3 times 5, a 1 over 5 times 7, and so on down the line.
Is there significance to pi over 4, or is that just...
No, there's not really a significance. It's just one that pops up a lot. This one converges a little bit faster to pi over 4 than the last one does. One of the things that's been a historical problem is finding different ways to approximate pi. So this is one of the ones that was found early on. Besides that little mess up there, which I don't know where I've messed it up, I'll type up an answer to this so you'll see it, so you figure out where I made the error. Is the idea behind what we're doing making sense? At least finding the coefficients? Yeah, Morgan.
So, like, I get find the coefficients, but, like, I'm kind of confused on, like, when you go and rewrite it. Like, you change, like, what we get from f of x, like, and you rewrite it to different form.
This is just trying to play around with getting different series expansions for different things. So, like the ones that you have in the second problem on the homework, that's the kind of thing that you want to do in there. I don't think those are as bad. I don't think you have to play with even and odd terms nearly as much. I think some good terms go away and the rest just sit in there. You can see them pretty quickly, hopefully. Really don't know why my That answer didn't come out right because I did it in my office and it came out just fine. All right. Again, for your project and those other, when the first part of your homework, don't spend a lot of time trying to get one of these nice formulas unless you're asked to do like the ones down lower in the homework where it says use one of the answers to help figure out that series expansion. Just go through GeoGebra, get that summation expanded so that you can see what the graph should look like. I can't remember which number I said to use. Oh, I didn't say. Yeah, for number one, I don't want you to try to find a closed formula. For number one, just do it all on GeoGebra and get an expansion and get a graph. That's all I want. Okay? So don't try. The second one's where you're going to have to try to find a formula for it. Okay? But like I said, I don't think that one will be as bad for trying to find the formula for it. All right. I do want to do one more thing. And like I said, we'll clean it up on Thursday we're eating pizza. Did I hit Excel? Let me get in my email real quick. Maybe. I sent everybody a file before class. Here we go. So, I made up a file that has a boatload of random numbers in it. And we'll talk a little bit more about how we can do more with this next time as well, but I just want to show you real quick the idea. If I actually attached a file, did I not attach a file?
It was there.
Yeah.
It's too big?
Yeah, that's what it says.
Oh, for heaven's sake.
It was too big to preview it.
It was a boatload too big.
How was it too big? It was just an Excel file.
Yeah, I tried downloading it and I never downloaded it through.
Okay. Now maybe I'll have to be a little more creative and put it on Moodle. It should be in here. What I won't. Come on. Oh, that's right. I'm in the right folder. Come on. I do enjoy when things don't want to run. I'll post the file on Moodle so we can get it downloaded that way. It'll be easier. All right, here we go. Seriously? What do you mean it cannot be found? Oh my gosh. Oh, there it is. Ha! Finally came up. It's because there's, I don't know, 50,000 random numbers in it, I think. You know what? Just do it this way. All right. I just want to show you the idea behind what we're doing. So say you wanted to take the integral from 0 to 1 of x squared dx. Now, obviously you know how to do this, but say you had a function you didn't know how to integrate. Okay. I certainly know that I can take that entire area, though, and put it in a box of area 1, correct? Right? I can certainly put it inside of a box of area 1. So what we can do is we can create some random numbers. The RAND function in Excel will create random numbers between 0 and 1. Let me just do a few hundred here to start with. Okay. Now what I want to do, these are points that will be in the square. 0, 1 for x, 0, 1 for y. Treat my A column as x's, my B column as y's. If I want to check if it's under the curve, y equals x squared, I would need the x squared, the a1 squared, to be less than or equal to the b1, right? And then it'll be under the curve, right? That would be the idea. So in C, what we're going to do here is say if a1 squared, what do I need? I want to make sure that I'm under the curve. So do I want to be, I want my y coordinate to be under the curve. So if my x coordinate here is 0.08, when I square it, I need that y coordinate to be under it. In this case, it's not, right? So if my a1 squared is bigger than my y, then my y coordinate that I generated is below the curve, so it's in the area that I want. So I'll call it a 1. Otherwise, it's a 0. Okay? So all we're doing here, oops, I don't know why I put, I went B1 there, sorry. I said Y and I hit the wrong thing. Sorry about that. All right, all that's doing is checking if this is my Y coordinate. If this is my Y coordinate, is it below Y equals X squared? I randomly picked an X coordinate, calculated it on the curve, Y equals X squared, and I'm checking to see if that randomly picked Y is below it. If it is, I'm going to assign it a value of 1. If it's not, I'm going to assign it a value of 0. And I'm going to count how many times this happens. So I'm going to copy this down. We've got 703 points here. That's good. I need to remember that. Let me go back up home. Okay. So we're going to count how many of those things in C1 to C703 are 1. There's 210 of them. Okay?
What did you put in for that last one?
This part, count if, and then I did the array, and I said it went down to C703. Okay? So I just counted how many numbers there were. Now it's 240. Every time you recalculate something in Excel, it'll re-randomize the numbers. So if I hit delete, there, it'll do it again. Okay. So now so what we did was we generated 703 random points. We calculated that how many of them are underneath the curve. That should tell us an approximation for the area. So if I take this number of points and divide it by the total, which was 703, I get 0.36. Or 0.34, or 0.34, or 0.31. I'm just basically doing simulations for what the integral might be. And every time it recalculates, it's just giving a different estimate for the integral using random points. Obviously, the more points you use, the better it should get to, the closer it should get to the approximation for the integral. But that's all you have to do. So if you have this bounding box around your area that you're trying to integrate, you select points in that bounding box, and you count how many are actually under the curve that's going through that box. And then the ratio of points that are in the box, or sorry, the points that are under the curve to the points that are in the box, should give you an approximation for the area. In this case, because the area was 1, if you have the area of the whole box, you have to divide by your area. But that's why you do what's referred to as Monte Carlo integration. That's an example of Monte Carlo simulation, using random simulation to try to approximate things. Which I thought was a really cool thing to be able to do integral. So we'll do a couple more examples while we're eating pizza next time. Okay? But again, it really is that easy. You just calculate random numbers, count how many of them satisfy the condition you want out of the total, and do a ratio, and it gives you the area. Or you can do double integrals and do volume, or do double integrals over a region and do volumes under surfaces and those kinds of things. So it's a cool little thing where all you're doing is just randomizing. So we'll do a couple more examples next time. Like I said, it's not a big deal. It's literally if you can make sure you check that you're in the region that you want to be, you can do integrals. So we'll talk about it next time. We'll see you on Thursday. Marcia and I will get together about